This clay tablet from between 1800 and 1600 BC shows that ancient Babylonians were able to approximate the square root of 2 with 99.9999% precision. How did they do it? First, let's decipher the tablet itself. It's time for Babylonian Math 101. This is called YBC 7289, short for the 7289th item in the Yale Babylonian collection, and it depicts a square, is diagonal, and numbers written around them. As the Pythagorean theorem implies, the diagonal's length for a unit square is the square root of 2. Let's focus on the symbols there. Babylonian mathematics used two symbols, the upright wedge representing 1 and the sideways wedge representing 10. Despite the two symbols, Babylonians used the base 60 number system. A single upright wedge means 1, two upright wedges mean 2, and so on. You can stack the upright wedges until 9, after which a sideways wedge is next, meaning 10. One sideways and one upright wedges mean 11, one sideways and two upright wedges mean 12, and so on. You get the rule. There are 16 digits in total. Let's look at the tablet. Along the diagonal of the square, 4 numbers are written: 1, 24, 51, and 10. In base 60, the number with these digits mean 1, plus 24 over 60, plus 51 over 60 to the 2, plus 10 over 60 to the 3, which is 1.414121, and so on in decimal. By putting the number from the tablet next to the square root of 2, we can see that they match up to the first 6 digits. The computational accuracy is stunning. The first time I heard about the Babylonian square root, I refused to believe it. But it's real. Let's talk about how they did it. Here's how the Babylonian square root algorithm works. First, I'm going to play the magician and describe the algorithm. I'll pull back the curtain afterwards and explain it all. We start by picking a number between 1 and the square root of 2. Let's call this x0. One such example is 1.2, which is going to be our first approximation. I know this feels random, but let's just roll with it for now. Because of its definition, x0 is less than the square root of 2. As the square root of 2 equals to 2 over square root of 2, we also get that 2 over x0 is larger than the square root of 2. In other words, the square root of 2 is somewhere between x0 and 2 over x0. Let's visualize this. Here's the real line, and there we have x0 somewhere between 1 and the square root of 2, and 2 over x0 between the square root of 2 and 2. If these two numbers indeed envelope the square root of 2, a logical next step is to take their average, which is what we'll call x1. And this goes on. Mathematically speaking, we define a recursive sequence by taking the average of xn and 2 over xn, where xn is the nth approximation. With our starting point x0 equals 1.2, that is 12 over 10, we have x1 equals 344 over 240, and so on. Let's visualize it for the first couple of approximations. As we can see, x3 is indistinguishable from the square root of 2 on this scale. We practically need a microscope to tell the difference. Our sequence converges to the square root of 2 extremely fast. But how fast exactly? Let's quantify it. We'll denote the approximation error by E sub n, given by the distance between xn and the square root of 2. Let's take a look at E1 and see what we can do. After we directly plug in the definition of x1, we can write the entire thing as one big fraction. Continuing the computation, we can notice that the denominator is a perfect square of e0. So, we finish with an estimation, obtaining that e1 is less than half of e0 squared. Repeating this argument, we obtain that the convergence is lightning fast, even faster than exponential. This is called quadratic convergence, doubling the number of correct digits in each iteration. Were the Babylonians just lucky, or did they hit the nail right in the head? The latter one. It's time to finally pull back the curtain. Let's talk about something called the Newton-Raphson method. Let's rephrase the problem of approximating the square root of 2. Instead of computing the square root function at 2, let's try to find the positive root of fx equals x to the power of 2 minus 2, which, as it turns out, is also the square root of 2. This is the same as solving the equation f of x equals 0. Computationally speaking, this is hard to do, as we can't take the square root. We don't know how to do it yet. So, the plan is to approximate f of x with a function that we can handle, and find the zero of the approximating function. A natural idea is to take the best linear approximation of f of x, which is given by its derivative. So we select a point x0 that is close enough to the square root of 2, and take the tangent line to the graph of x at x0, which is given by f of x0 plus the derivative of f at x0 times x minus x0. This intersects the x-axis somewhere around the square root of 2. The next step is to find where this intersection is. This is done by solving a simple linear equation for x, obtaining that x equals x0 minus f of x0 over f prime of x0. We can easily compute this expression in practice as well. Thus, by selecting our next guess x1 as this intersection point, we obtain a hopefully better approximation. And here we go. We can define a recursive sequence based on this idea. This is called the Newton-Raphson method, sometimes also Newton-Raphson iteration. Here is the next step, and the next step. As you can see, we are almost at the square root of 2. So, we have seen two ways to approximate the square root of 2. The general Newton-Raphson method and the Babylonian algorithm. Which one is better? First, let's revisit the Newton-Raphson method and find an explicit expression for approximating the square root of 2. Our function, whose root we want to find, is given by f of x equals x to the power of 2 minus 2, while its derivative is given by f prime of x equals 2 times x. The recursive sequence is defined by xn minus f of xn over f prime of xn. After unwrapping f and f prime, we obtain a fraction. We can continue the calculation by bringing the two terms together via a common denominator. After clearing up the resulting expression, we get a familiar one. This means that the Babylonian algorithm is a special case of the Newton-Raphson method. Recall that the convergence is extremely fast in this case. Is this true in general? Only if we are lucky. Unfortunately, it's not all perfect. The Newton-Raphson iteration can fail miserably in certain not-so-rare cases, and there are several drawbacks. For instance, if the function is flat around the root, the convergence can be painfully slow, as the example illustrates. Moreover, the entire process depends heavily on the initial guess. The iteration might converge to the wrong root, or even diverge. It is pretty stunning that the ancient Babylonians were able to compute the square root of 2 up to the 6th digit. This accuracy is extremely respectable, especially considering that it was achieved almost 4,000 years ago, computed entirely by hand. As it turns out, they were not merely lucky. They stumbled upon the special case of a powerful method able to approximate the root for a wide array of functions. This became known as the Newton-Raphson method. If the function behaves nicely enough, like in this case, the convergence is extremely fast. This is why the Babylonians were able to achieve the greatest known computational accuracy in the ancient world. Thanks for watching, and see you in the next video. Cheers, Tivadar.